This section is 3.2, and it is about linear functions. So we talked previously about what the definition of a function is, right? We talked about relations, and then we talked about functions being a relation where we can't have two of the same inputs, right? We couldn't have a repeated x, or we could use the vertical line test to determine whether or not a graph is a function, right? If it passes the vertical line test, it means that a vertical line only passes through one point on that function anywhere that you would draw a vertical line. So today we're going to talk about a specific type of function, which are linear functions. Okay, so a linear function is typically written in two variables, x and y. Linear function is written in two variables, x and y, and it can be written in the form as y equals mx plus b, where m and b are constants. So these would be numbers. So what it would look like when it's actually written, sort of as a function with numbers is something like y equals 2x plus 5. Something like that. So that's a linear function. Okay? The graph of a linear function is a non-vertical line. A non-vertical line. Okay? It must have a constant rate of change. And we'll look at some examples of this later. Remember, if the graph is a vertical line, it wouldn't pass the vertical line test, right? Which is why it has to be a non-vertical line. If it was a vertical line going straight up and down, it wouldn't pass the vertical line because if you put a vertical line over it, it would hit every single point on that graph rather than just one. Okay, so non-vertical line, constant rate of change. Okay, a nonlinear function, so the opposite of this, graph of a nonlinear function will not be a line. Oops. It might have curves. It might change directions. And it might not have a constant rate of change. So if you see any of these things, it's not a linear function. It's nonlinear. For it to be linear, it must be a non-vertical line, it must have a constant rate of change. So it will look like a straight line, right? It might be going diagonally, it might be going horizontally. It will never go vertically, but as long as it looks like a straight line, either diagonal or horizontal, then it's a linear function. Okay? For example, starting with looking at graphs. Okay? It's going to ask us, does the graph represent a linear or a non-linear function? And then they're going to give us a couple examples. All right, linear or nonlinear. The first example they give us looks like this. And we are to determine whether this graph shows us a linear or a nonlinear function. Okay, if we're saying that the graph of a linear function must look like a line, it cannot have any curves, it cannot change direction, it has to be a straight line, we can see that this shape of the graph is curved, right? It's still a function, it passes the vertical line test, but it's not a linear function because the shape of this graph is not a line, it's not a straight line. Instead, it's a curving shape. So we would say that this is non-linear because it's not a straight line. It's a curve. Okay? Versus this function. Is this linear or nonlinear? This one is a straight line, right? It's going diagonally, but it's still a straight line. It does not contain any curves. It doesn't contain any changes of direction. It's going in one continuous direction. So this is a linear function because its graph is a line. And you can see in that word linear, the word line, that's our clue, what these should be looking like. Okay. The second way that we can identify linear functions is through tables. Okay. Like we said before, linear function must have a constant rate of change. So x increases or decreases by the same amount. And y also, your y values will be increasing or decreasing by the same amount. Okay, if they're not, then it's not linear. You have to be adding or subtracting the same amount. So let's look at a couple of examples. This is example 2, and we'll be given some tables here. So letter A gives us this table. And we'll have x and we'll have y, and we'll plug in values there. Well, we won't plug in values, they'll give us values. So here we have x, 3, 6, 9, 12. And y, 36, 30, 24, 18. And they're asking us again, is it linear or non-linear? So in order for it to be linear, x and y, so the x values must be increasing or decreasing by the same amount, and your y values must be increasing or decreasing by the same amount. Now, the x values don't have to be increasing or decreasing by the same amount as the y values. So we just look at x by itself, and then we look at y by itself and ask ourselves, are they increasing or decreasing by the same amount? So looking at our x values, we can see that between each x value, as we're increasing, we're going up by 3 each time. It's a consistent, so good. Our x value is increasing by a constant amount. We look at our y values and we see that y is decreasing by 6 each time. So x is constant, y is constant. So we would say that yes, this is a linear function because it's a constant rate of change. As x increases by 3, y decreases by 6 every time. X goes up by 3, y goes down by 6. X goes up by 3, y goes down by 6. So this is a constant rate of change that is happening every single time. Look at letter B. It's another table. It's not the most even table, but bear with me. All right, in this case, we've got x, 1, 3, 5, 7, and y we have 2, 9, 20, 35. It's asking us the same question. Is this linear or nonlinear? So let's start by looking at our x values. All right, from 1 to 3, we're going plus 2. 3 to 5, plus 2. 5 to 7, plus 2. So far, so good. Our x values have a constant rate of change. Then let's look at our y values. 2 to 9, plus 7. 9 to 20, plus 11. 20 to 35, plus 15. This is not a constant rate of change. Okay, our x is constant, but our y is not a constant rate of change. It changes each time it goes up. Okay, so this is not a linear function. We would call this nonlinear because the rate of change isn't constant. It changes each time for y. Okay, this doesn't mean that there might not be a pattern, right? Maybe there's a pattern here. That's not what it says. It says that it has to literally be a constant rate of change in order for it to be linear. It has to be the exact same change every time. So this is nonlinear because it is not the exact same change every time. All right, the other thing about functions, so initially we said linear functions must be able to be written as y equals mx plus b. Right, so you have to be able to write it in this form. Notice the important things here are y is by itself and positive, and it has no exponents. Same thing with our x. Okay, it has no exponents, it's in the numerator, and we're not sort of manipulating this in any way. So it's just sort of a straight y, it's a straight x, it's got maybe a, constant in front of it, so something like y equals 4x minus 1. Notice our y and our x haven't changed at all. It's still just y, it's still just x. Yeah, they might have a number in front of it, but we haven't changed the exponents or sort of the position of the x or the y to be in a numerator or in a denominator. So, a couple things that we're going to look for. Okay. A linear function could be that y equals x. It could be that y equals a number. So for example, y equals 2. That's a linear function. A couple of things that it cannot be. X cannot be taken to a power other than 1. So notice here, x is just to the first power. It's not squared, it's not cubed, it's not to the 10th. Okay, same thing with y. Y isn't taken to the first power. So we can't take it to a power other than 1. Also, we cannot have any square roots. No square roots as part of linear functions. So no exponents, no square roots. The variables cannot be exponents. Okay, so for example, let's look at what a non-function would look like. This would be something like y equals x to the third. That's not a linear function. This is not a linear function. Y equals the square root of x, right? That's not a linear function because no square roots. We cannot have variables in our exponents, so something like y equals 3 to the power of x. That would not be a linear function. And we also cannot have variables in denominators. Okay, no variables in the denominator. So something like this, y equals 2 over x, that would not be a linear function. It has to be able to be put into this y equals mx plus b form. No square roots, no exponents, no variables in the denominator. Okay, so just watch for those. All right, let's go ahead and look at discrete domain. We talked about this a little bit when we did domain and range. So remember, a discrete domain consists of points. Discrete domain consists of points rather than sort of a continuous line. So, for example, this one gives us a word problem, and it asks you to look at word problems and determine whether the domain is discrete or continuous. So, it consists of points. The values cannot be broken into smaller parts. Okay, for example, this is going to be example 4. We skipped example 3 because it was just being able to identify whether or not equations were, I sort of worked example 3 into my examples of, y equals mx plus b. Okay, so we're just moving on to example 4. Example 4 is a word problem, and so what it says is the linear function, and it gives this to you, y equals 15.95x, represents the cost, y is the dollar amount, okay, of the cost, for x number of tickets. Okay. If you're going to museums, so it's y equals 15.95x. This is the cost, the total cost, and x is the number of tickets. So what it's going to say is each customer can buy a max of 4 tickets. And then it asks us the following. A, find the domain of the function. Find the domain of the function. Is it discrete or continuous? So with this, in order for us to determine whether it's discrete or continuous, remember the domain of a function is all of the x values, okay, for which the function exists. In this case, the domain, the x values are tickets, and it told us we could buy a maximum of 4 tickets. Okay? Now, determining whether the domain is discrete, meaning it's sets of points, or a line, depends on whether we can break this domain, the value, into smaller pieces. So what we're asking ourselves here, our domain is tickets. And how many tickets can one person buy? Well, a person could buy 0 tickets, they could buy 1, they could buy 2, they could buy 3, or they could buy 4. But you would not be able to buy pieces of a ticket, right? You couldn't buy 1.5 tickets or 2.27 tickets. You have to buy whole number tickets, meaning that this domain, if we graphed it, would be discrete. We'd only have points at 0 when x was 0, when x was 1, when x was 2, when x was 3, and when x was 4. Because we can't break that domain, we can't break those tickets into smaller portions. So I'm going to sort of set up a little graph here. Okay, along my x-axis I have sort of 1, 2, 3, and 4. Right? That's going to be my domain. And I also have 0 here at the origin. Right? I can then graph this function using the domain values. Right? Because what I can do is I can plug in each x here and get an output. So let's go ahead and do that. I'm going to make a little function table here. And I'm going to plug in 1, 2, 3, 0, 1, 2, 3, and 4. Okay, if I buy 0 tickets, I plug this back into my original equation. I know that each ticket is $15.95. If I buy 0 tickets, how much money did I spend? Well, 15.95 times 0 is 0. I didn't spend any money. So my first point is here at 0, 0. Okay, and then I'm going to just sort of plot points. Oops, I should do this in black. I can see that my domain is kind of going to go up by 16s. 48 plus 16 would be 64, and then 80, I guess. Okay. To graph the rest of these, I'm just going to plug in each domain number. 15.95, if I bought 1 ticket for $15.95, I would pay $15.95. So I can graph this point here at 1 and 15.95. If I buy 2 tickets, I'm paying $31.90. So 2 is at 31.95. Okay, 3, I would do 15.95 times 3. If I bought 3 tickets, I'd pay $47.85. $47.85, so right up here. And if I bought 4 tickets, I would spend $63.80. Okay, so what I'm doing is I'm plugging my x in up here, and I'm getting an output. And that's how I graph based on the domain. So this one's at 63.4 and 63.80. Okay, and the domain is discrete, and then this is part B. This is our graph. It's discrete because I can't break these tickets down into smaller pieces. All right, the last one, example 5, gives us an example of when the domain would be continuous. So this one says a cereal bar contains 130 calories. The number of C calories is a function of B, bars eaten. All right, so it says, does this scenario represent a linear function? And why? So think about this. We could sort of try to model this using a little function table, right? If we have B bars that you eat and C calories, we can try to sort of model this using numbers. If you eat 0 bars, how many calories do you consume? Well, 0. If you eat 1 bar, how many calories do you consume? Well, each bar is 130, so you consumed 130 calories. If you eat 2 bars, you consume 260 calories, and so on and so forth forever, right? Unless it tells you how many total. Now, with this one, could you consume, like if this is our domain, right, our B values, how many bars you consume, could you consume a portion of a bar, like a half a bar? Yes. If you consumed a half a bar, you would only consume, what's half of 130? 26 calories. Right? And could you consume a quarter of a bar? Yes. And you could calculate sort of varying amounts of the bar that you consume because you can break it into smaller pieces. So this is a constant rate of change that we're seeing. So this would be, yes, a linear function. So we could see that it was a linear function because as it was going up by 1, right, in our B column, it was going up by 130 in our C column. We could break this into smaller increments that still make it a linear function. As it's going up by a half, it's going up by 26 or whatever. So this is an example of a linear function. The second question asks us the domain of this function. Now, we talked about the fact that this is not, we can break a cereal bar into tiny, tiny little increments, right? Like crumbs. If you ate a crumb of a cereal bar, you might be eating like, you know, a 1/16 of a calorie or something. But it's still, it's unlike a ticket in our last example. You are able to break it into small, tiny, tiny pieces and find little percentages, right? Sort of decimal, fractional portions of that cereal bar. So this is a continuous domain, right? It's a continuous domain because you don't have to break it into whole numbers. We can break it into little fractions. We can have pieces of a cereal bar. So it's continuous domain. And we can write this domain as the cereal bar. You could eat any amount greater than 0. Right? You can't eat less than 0. You can't have less than a cereal bar, but you could eat 0 cereal bars or any sort of increment of cereal bar up to whatever, infinity, if you were really going for it. And then the last part is they say graph the function using its domain. So if we were going to graph this, we take these input values and you can choose, you know, I would say maybe 3 values to graph. And so we input our x, which in this case is our b value. I'm going to choose these ones that we did initially and graph these points. Okay, so we would have 1, 2, 3, 4 if we went that way. And then I'll do my y-axis by increments of 130 because that's a whole cereal bar. Okay. For this one, when I graph, I start here. If I eat 0 cereal bars, I've consumed 0 calories. If I eat 1 cereal bar, I've consumed 130 calories. If I eat 2, 260, 3, 390, and you can see how this is going. And you can also see the shape of this function. It's linear. But what's different about this graph is that because it is continuous, I will connect those dots. And this line could go infinitely higher. right? Because you could eat infinitely many more cereal bars. And they didn't give us a stopping point. So we just draw the line with an arrow going to infinity. All right, that is it for this lesson.